Hi, Year 10. So, just a wee quick reminder about what we were doing last week. If you remember, we had our wee semicircular glass block and we were shining light into it and seeing what happened to the refracted ray whenever we changed that angle of incidence a lot. So, we did our first one, shining our incident ray in here.
I didn't get that. Could
you
try again?
We started here shining our incident ray in at 30 degrees, and then we measured our angle of refraction and we recorded that over here in this table. Then we increased our angle of incidence to 60 degrees, and that's this green line. And what we discovered there was that no light actually got refracted outside the glass block. It all got reflected inside. So this wee edge of the glass block here actually ended up acting like a mirror and not allowing the light to pass through. It was just reflecting the light back inside it. Okay, so that's why we didn't record an angle of refraction there. And then the law of reflection would apply here, so whatever your angle of incidence was, your angle of refraction would also be that. Then we took measurements to see what angle of incidence was like the cut-off point for that to happen. So there is an angle of incidence where your angle of refraction will be 90 degrees. So as we increased our angle of incidence here, like from the yellow one on round, this ray of light here would have got refracted more and more and more and more until eventually that angle of refraction was 90 degrees. So the angle of incidence that gave us that angle of refraction of 90 degrees has the name of the critical angle, and for glass it's 42 degrees. Now, then we discovered that any angle greater than that critical angle here, we would get total internal reflection. So at 43 degrees we would get total internal reflection, at 45, at 70. Any angle greater than that is going to give us total internal reflection and no light will get refracted outside of the glass block. So we summarise that down here. So this here would be like the definition of critical angle. So the critical angle is the angle of incidence that gives an angle of refraction of 90 degrees. And then we just made a note of what the conditions really that are necessary for total internal reflection to happen. So if the angle of incidence is greater than the critical angle, all light is totally internally reflected. And this here is an important point. This only happens whenever the light would be travelling from more dense towards less dense. So for here, we were in the glass and the light was travelling towards the less dense air. Now, that was the experiment that we did. I had asked you then to answer the questions on page 81. So if you get your page 81 open in front of you, and you can mark and correct this for me. So for question 1, what was the difference between what happened to the ray at 30 degrees and what happened to the ray at 60 degrees? So when the angle of incidence was 30 degrees, the light was refracted, so just normal refraction happened. But when the angle of incidence was 60 degrees, the light was totally internally reflected. For this one here, what was the critical angle? I'd asked you to write down the size and the definition. So the critical angle size here was 42 degrees. So correct that if you maybe wrote that down wrong. I think a few people wrote 60. And then for the definition of critical angle, the critical angle is the angle of incidence that gives an angle of refraction of 90 degrees. Summarise the results of your experiment. Now, I will admit some of your answers here are better than mine, more detailed. So I summarised it like this. Angles of incidence up to the critical angle, which was 42 degrees, caused the light to refract out into the air, just as normal. A better answer there would have been to say to refract and bend away from the normal out into the air. Angles of incidence greater than the critical angle caused light to be totally internally reflected inside the glass block. Now, I really should have added in there, and a couple of people did, and I was loving it, that this only happens whenever the light is travelling from more dense to less dense. So I'm going to add that into mine now. So there we go. This can only happen when light is travelling from more dense to less dense material. Okay, now let's move on and have a wee look at what we're doing today. So turn over to 82 for me, please. We're just going to be looking at total internal reflection again today. Little tiny bit about the uses of it. And then there's some questions to answer. So I'm just going to read through these notes and then add in little bits as we go. So Sometimes light rays never leave the denser substance. So I'm just going to keep referring back to this diagram here, okay? So that would be like this green line. Whenever the angle of incidence was greater than the critical angle, then the light doesn't leave. Now, this one was able to leave over here, but that's because it was hitting the surface at 90 degrees. If whenever it got totally internally reflected here, it hit this surface at an angle of incidence greater than the critical angle, then it's going to get totally internally reflected again, and that's going to keep on happening. And that is actually what you can see happening down in this wee diagram here, okay? So the light's traveling along here, it's hitting at an angle of incidence greater than the critical angle, it's going to get totally internally reflected. That happens again here and here and here. So even though we have this like curved material, the light can still actually travel along it, even though light travels in straight lines, because you can see it's just keeping on getting totally internally reflected the whole way along here. So that's quite cool that we can actually see light going in curves, even though the light itself cannot travel in a curved line. Anyway, I've digressed. Right. So diamonds sparkle because the faces are cut so that light is totally internally reflected. So yeah, that's why I'm just repeating it. That's why diamonds sparkle, because the light just keeps on getting totally internally reflected. Optical fibers use total internal reflection, so we are all using a lot of optical fibers at the minute, with all the internet we're using right now. So these are very thin, flexible glass rods, so light reflects internally along their whole length. This means that any image at one end of the fiber can be communicated very clearly to the other end. So if we had an image here, then that data, that like information, can get transferred the whole way along, and then it can be projected out at this other end, okay? So another really good use of optical fibers is to see inside people, okay? So it used to be like if a doctor wanted to look inside, they would have to always cut you open like a proper operation, but now they're able to see inside with just a very, very small incision. So something like a keyhole surgery could be done that way. The other thing that it can be used for that within that regard would be endoscopes. So if anyone's ever had one of those like cameras put down their throat, that's making use of total internal reflection. So the light would get shone down inside you, would light up inside, and then there would be little absorbers that will collect the reflected light and transfer that information back to the computer so that the doctor can see inside without having to open you up, okay? Now, I must admit, I haven't really written much of an explanation here, so short explanation for each one. Uses of optical fibers, these are the two big ones. So fiber optic broadband, which means we're able to transfer large amounts of data relatively quickly, and the endoscope, and that's to see inside a patient's body easily without having to cut them open. Okay, over onto page 83 for me, please. There's some questions eventually. This is all kind of like just notes, and then there's some questions. So when light rays are transmitted through a glass block, they don't always pass right through the block and back out into the air. Sure, that's what we discovered last week. Sometimes some of the light is reflected and some of it is refracted. So this is our normal situation, like our 30-degree one, our 30-degree angle of incidence that we did last week. Okay, so our light just gets refracted, bends away from the normal, but a little bit does get reflected back inside. Now, once the angle of incidence increases to a certain amount, then we know that the angle of refraction is 90 degrees, and this angle of incidence that gives us the angle of refraction of 90 is called the critical angle. We wrote that definition down on that experiment page last day. That page is important for you to keep, okay, with those important definitions on it. I was going to get us to write them out again, but if you just keep that experiment page, that's what you would write in an answer in an exam. Now, then we know that if the angle of incidence is greater than the critical angle, then no light gets refracted out the outside, it all gets reflected back inside, and that's called total internal reflection. And remember, the law of reflection still applies here, so the angles of incidence and the angle of reflection are going to be the same size as each other. So total internal reflection can happen whenever light goes from water or glass into air, and it has many applications. So here's a couple here, we'll have a wee read through these. So telescopes and binoculars. So most telescopes use 2 lenses. Now we are not learning about lenses this year, I don't think so anyway, no. But you'll do a bit about lenses in GCSE if you come on to do GCSE physics. So most telescopes use 2 lenses to make a larger image, but the image is upside down. Binoculars have 2 lenses and 2 prisms. The prisms send the light backwards and forwards 3 times, so binoculars are shorter than a telescope of the same strength, like for the same amount of magnification. The prisms also then make the image the right way up, so if you sit, again you'll have to pause me and follow the rays of light, you should see that the light is going to end up being the right way up. Some telescopes have been specially designed for bird watchers, and these telescopes have arrangements of prisms to turn the image the right way up. Although these telescopes give better magnification, they're much heavier and they're much more expensive. So that's why bird watchers will generally use binoculars. There we go. Optical fibres then, what we were talking about a little bit earlier. So doctors can use glass fibres to see into different parts of the body. Light is reflected from side to side along the glass fibre, and when glass fibres are used like this, they're called optical fibres, because optics just refers to light. So we can see here the light just getting totally internally reflected the whole way along there. Now I'm going to link as well a wee video that is going to show you this like uses of total internal reflection, which will be a bit more interesting than listening to me rambling on. I'm almost done, I promise. Now, I would like you to give these questions on page 84 a go. You might find some of them difficult, but I just want you to try your best. Okay, so let me have a wee look and see if there's any I need to give you any wee hints for. I think 1, 2 and 3 I'm going to leave to you. Just be careful here with these prisms. Remember, if I was answering this, I would probably rotate my page around. I would mark my normal on and have a think about what size that angle of incidence is, and then what that means is going to happen to the light. This last wee one, I'm not sure if you know what periscopes are. It might be easier to Google it, but like, do you know those wee things that like people in submarines could use? So I'm acting like I'm holding it, but you look in here and then there's prisms totally internally reflecting the light inside, and then like there would be a thing away up here, and it means that I can be at this level and be able to see something way up high. Or if it was sideways, I could be sitting here and then the light would be getting reflected like towards me from all the way over here, so I'd be able to sneakily see around a corner without people seeing that I was there. Yeah, but it's probably easier to Google a periscope, not the app, but like the actual physical thing, periscope. Don't even know if that app is still about, to see what we mean by that. Okay, so show us your page 84 filled out and watch that video that we're going to link as well. Okay.